Hello and welcome to today's lesson where we're going to look at a practical to determine the wave speed of a wave in a solid. So in today's lesson we're going to try and understand how to calculate wave speed of a wave in a solid, calculate wave speed from experimental values and explain why different measurements are taken and how this takes place, which falls into the following part of the AQA GCSE Separate Science Specification 4.6.1.2 Properties of waves, and in particular it's looking at a required practical, which is where you've got to make observations to identify the suitability of apparatus to measure frequency, wavelength and speeds of waves in a ripple tank and waves in a solid by taking appropriate measurements. So in previous lessons we've looked at the idea of wave speed. The wave speed is the speed at which the energy is transferred through a medium. It is the distance a wave covers in 1 second. Now all waves have a wave speed, and the wave speed for all electromagnetic waves is the same, 3.0 times 10 to the 8 meters per second when it's traveling through a vacuum. Now an electromagnetic wave is a vibration in the electrical and magnetic fields that permeate through our universe. Now the wave speed for a mechanical wave depends on the medium it is in, whether it's in a solid, a liquid or a gas. Now a mechanical wave is a vibration of particles in a material. Now mechanical waves tend to travel the fastest in solids and the slowest in gases, as it is easier for the vibration to be passed on in solids compared to gases. Now the most common example of a wave in a solid material in the real world is a seismic wave traveling through the earth, but other examples could include waves on guitar strings or waves on wires. Now in a seismic wave will be a wave that's produced after an earthquake has occurred on earth. Now the wave speed, which is the speed the wave is traveling at, or the speed at which energy is transferred through the medium, can be calculated with the equation wave speed is equal to frequency times by wavelength. Now in today's required practical we're going to measure the wave speed for a wave in a solid medium. So this means we'd need to measure frequency and wavelength and then multiply the two values together to calculate the wave speed. So in the investigation today, in this required practical, the practical you must know for your GCSE examinations, we are going to look at how you calculate the wave speed of a wave in a solid from measurements of wavelengths and frequency. So you would need a vibration generator, a signal generator, a string or a piece of cord, a set of 100-gram masses and a hanger, a set of 10-gram masses and a hanger, a wooden bridge and a pulley on a clamp. And you set up the apparatus as we can see in this particular diagram, with the vibration generator at one end of a string and a set of masses at the other end of a string, all suspended by using a wooden bridge and a pulley. So you would switch on the vibration generator, which would make the string or elasticated cord start to vibrate. You would then see a clear wave pattern and then adjust the tension of the string or move the wooden bridge to adjust the length of the string, and the wave would look like then it's not actually moving. Now you would then use a meter ruler to measure across as many half wavelengths as possible, then divide by the total number of half waves, and then you multiply this number by 2 to give the wavelength. The frequency of the wave is the frequency stated on the signal generator, and you can calculate the wave speed of your wave by doing the equation wave speed is equal to frequency times by wavelength, and you repeat those steps for different frequencies which can achieve different numbers of complete waves on a string. So just to show you what we mean by this, you would set up this particular apparatus over about 2 or 3 desks. So you set a pulley up to place the string through at the end of the table. You would then attach the length of string to a vibrator and a signal generator, and then the pulley as such, like that. So you've got your vibrator, your signal generator and your pulley. Now the signal generator is turned on to ensure the string vibrates, so it produces a wave on the string. Now this would be a mechanical wave, as it is due to the particles in the string vibrating that there is a wave in place. So the generator produces a wave which progresses through the string. So you've got your wave as such. Now if we alter the frequency of the signal generator, we can alter the number of complete waves per second produced on the string. Now this is the principle which allows stringed instruments such as guitars to play musical notes when they're plucked. And in addition, this explains why holding the string at different positions with your finger produces different notes on stringed instruments. Now in this particular situation, you've got to be able to measure the frequency and you've got to be able to measure the wavelength. Now the wavelength is the length of one complete complete wave, the distance from one place on a wave to the same point on the next wave. Now this could be peak to peak or trough to trough. Now this means that one wavelength is going to be two loops on a string, because it's the distance between those two loops, in this example 2 peaks, which give us that wavelength. So one wavelength on a string will be shown by 2 complete loops, 2 wavelengths on a string will be shown by 4 complete loops, 3 wavelengths on a string will be shown by 6 complete loops, and 4 wavelengths on a string will be shown by 8 complete loops. Now what you can do is you can use the complete length of the string to find out the wavelength of the wave produced. So for example, if you know that there are 8 loops on your entire length, you can divide the entire length of the string by 4 to get your value of one wavelength. Now we can then use this wave on a string to measure the frequency by looking at the signal generator and seeing what frequency it's set at, and then we can use that to measure the wave speed. So what you would do is you would take your measurement of frequency from your signal generator, you would calculate your wavelength of the wave produced by using a ruler and look at how many loops were on a string at that point. You then multiply the two values together and you would get the wave speed of the wave. Now in theory, if you change the frequency, the wavelength would alter to ensure that the wave speed would stay constant throughout the investigation. Now the value for the wave speed achieved for different frequencies might actually vary slightly due to experimental error that takes place in the investigation. But in theory, if you alter frequency, wavelength would alter to ensure wave speed stays constant, and if you altered wavelength, frequency would also alter to ensure wave speed remains constant throughout the investigation. So what have we learnt in today's lesson? Wave speed is equal to frequency times by wavelength, and you should be able to recall and apply this equation. And then you should be able to make observations to identify the suitability of apparatus to measure the frequency, wavelength and speed of waves in a ripple tank, which we'll look at next lesson, and the waves in a solid, and take appropriate measurements. So if you've been successful and you've learnt in today's lesson, you understand how to calculate the wave speed of a wave in a solid. You can calculate wave speed from experimental values, and you can explain why different measurements are taken and how this takes place. I hope you've enjoyed today's lesson where we've looked at the practical to determine the wave speed in a solid, and have a lovely day.